So I'm Sadhana from IIT Bombay, and I'm an experimentalist. I did my PhD in STAR experiment at Brookhaven National Lab with Rick Accelerator. And currently I'm working in ALICE experiment at the Large Hadron Collider. So totally focusing on the heavy ion aspect at collider energies. So today so first of all, I would like to thank the organizers to give me this opportunity. Although I'm not an expert in EIC physics or something, but I would like to focus on the ion part of the electron-ion collider. So maybe the first half of the talk would be very cliched and boring because you all are experts, but I have to set the stage. So I have put some basic ingredients before we go to why we need to do electron-ion collisions. So the outline would be why EA collisions, why we need this A in our collisions, and a little bit of PDF and NPDFs. It's not exactly a big, let's say, theoretical input, but what we see. And then third, I will be talking about the initial states in heavy ion collisions. So towards the end, I would like to set the stage for the heavy ion part of this talk. Okay. So it's exactly a century more than when Rutherford discovered the protons. And if you remember in our school days, when we first studied about these protons, our teachers used to tell us that it is a featureless ball having a unit positive charge. And we were quite happy with that, right? Then some of us thought of continuing this in our college days, where it was really revealed that, okay, they're not featureless balls, but they had substructures. So they are now composed of, let's say, fine particles like your quarks. And okay, we are happy with that picture too. But now, with advent of research and experimental results, we see that even it's more than 100 years of its discovery, and we have not quite understood it. So it's becoming very complicated day by day. That's how the structure of proton is coming to us. Now let's see what happened. Initially, we had this pattern model of protons, which we still teach to our students. When we talk about the proton wave function, we tell them that it is a superposition of up and down quarks, correct? And then after this Rutherford experiment, the problem with this proton is that, or let's say this hadron is that, it has now become a quantum mechanical object with a haze of probabilities, right? Now, it depends upon the experimentalist or the setup of the experiment, and then it reveals a different structure. Okay, so if I go back to the Rutherford area, it will still be a featureless ball. Then I increase my energy and I go to elastic scattering. Then it will show, okay, it's not a point object, but it has a structure. Then I increase my energy more. What was done at SLAC? So what they did, they could hurl electrons forcibly, okay, by increasing the energy so that it could shatter the proton, okay. Now the electron, via the virtual photon, it could interact with the shards of the shattered photon, and we knew that it was made up of quarks. Okay, now then we again increase the energy. That's what we are having at Hera, which is like 1,000 times more than what we had at SLAC. Now it can show that this simple picture of, let's say, 3 quarks is also not valid. Now let's see what happens. Now because once we have different scattering experiments, we also have this multitude of collision aftermaths, right? So we'll have different particles, or let's say different electrons coming at different energies. So let's focus on this very nice diagram. So the structure is revealed as per what the electron faces inside the proton. So let's say if it bounces back from a quark which carries, let's say it has 3 quarks, so the energy is such that it gets bounced off by quark which has 1/3 of the total proton's energy, then we see a structure which has like 3 quarks, right? This is what SLAC gave us from the deep inelastic scattering. Now, with the Hera collider, what we see now, if the electrons are, let's say, glanced off by a quark, or let's say a parton having carrying very small momentum of the total proton, then we can see that the feature becomes from 3 quarks, we have multitude of partons. We have countless gluons and sea of transient quarks and antiquarks popping in and out. This is the picture which is Hera giving us. Now suppose I try to accelerate the proton more so that now my electron glances off from a parton which has which carries a very small fraction of the total momentum, then we'll see that this picture's becoming more blurry and we see it as a gluon dandelion. Okay, it's like cloud made up entirely of gluons. So this is the picture emerging as we are changing the energy and as we are seeing different, let's say, outcomes of the collision. Now recently, I think so it's in 2022, we saw a very different picture which tells that the proton wave function can have superposition of Schwarm quarks which are heavier than protons itself. So we can see that as we are, and this is something, this is a paper, very nice paper which tells about that, and it's from the NN-PDF collaboration which took the data for last 50 years and all, and they did some analysis using machine learning techniques and they give us this picture. So the proton, I mean, the search is quite humbling because once we try to search more and more, it is giving us new things to search for. Okay. So basically the QCD is studied by deep inelastic scattering, and this is what you have for last 2 days. You know everything about this deep inelastic scattering. So when we saw that gluon dandelion picture, the idea is that the gluons, I mean, can pick up some energy fluctuations inside the hadron, so, and they can break into a quark and anti-quark pair, which then annihilate back. So there's these fluctuations going on, but how to catch that picture, or how to take the snapshot of that picture? So the idea is this, something is happening. Now, if we try to accelerate our proton at ultra-relativistic energy, so what will happen? So due to the Lorentz time dilation, so these gluon fluctuation, so the time, due to time dilation, we can see them for a longer period of time. Okay, so that will help to take snapshots of the structure if we are able to accelerate protons to velocities close to the speed of light. Okay, so by whatever probe, let's say it's a lepton or something, that will reveal that structure, what we used to see, I mean, and this structure will be helpful to see, let's say, the gluon dandelion picture, which is predicted by QCD. So the two important parameters in, let's say, kinematic parameters in deep inelastic scattering are the Q square and the X, Bjorkian X. Q square, as you all know, it's the photon virtuality, and it is indicative of the transverse resolution. So higher the Q square or higher the Q, we can really probe the smallest r that comes exactly from your Heisenberg's uncertainty principle. Then we have this X, which is the Bjorkian X, which tells us about the fraction of the proton momentum carried by the struck quark. So if you go, as you know, if you go lower and lower in X, you are essentially probing high scattering events, and that will give us the picture of the gluons. So now once we are probing the structure of the proton, so it is essential to see how the partons are distributed inside the proton. Now, as we know that the protons consist of these partons. So we also need to see the structure of this proton by usage of this parton distribution functions about which you had already known. So let us give a very easy definition to that. So it's the probability to find, so PDF, so you can imagine as a probability distribution function also. So these are the functions which give the probability to find partons inside a hadron, and it's normally shown it is as a function of proton's momentum carried by the parton, and that is your x, small x. And this virtuality of the photon, okay, which probes your hadron, it determines also the size of the transverse region, okay. And both these two quantities are required to know the proton wave function. So we can say that the proton wave function depends both on Bjorken x as well as the virtuality. Now let's see in this figure the parton distribution function of a proton, a very generalized experimental diagram. So what we can see that the PDFs of valence quark in the proton decrease with increasing x, okay, decreasing x, okay. So if you see for U, D, which are the components of the proton as we see in the parton model, so as you go lower in x, you see the probability or the probability of finding those let's say constituent quarks are less. While this is becoming less, but if you see the PDF of C quarks and the gluons, they grow very strongly. So if you see that, one has to really scale down just to fit into this picture. So what you see that the gluon distribution dominates over valence quark, these are the valence quark, as well as the C quarks at very low x. So at low x, part of the proton wave function responsible for interactions in high energy scattering consists of gluons. So remember, when it's low x, it's high scattering, and whenever we are seeing that proton, that is essentially made up of gluons, or it's essentially consists of gluons. Okay, with that, and this is something which shows that transition. So this is your proton at a low energy, then you go to very low x or high energy. So then you see many new smaller partons are produced. So this small x proton wave function is dominated by gluons. This is important because we are going to come back again when we talk about the initial state of the nucleus, okay. So you see that the small x proton wave function is dominated by gluons, which populate the transverse area of proton. I'm talking about transverse area because at those relativistic high energy, your proton would look like a pancake, okay? And creating this high density of gluons, this small x wave function of an ultra relativistic proton or nucleus, because nucleus is nothing but let's say a proton molecule, it is known as the color glass condensate. We'll talk about this later when we'll discuss about the initial state of heavy ions. Now once we know this parton distribution functions, so as per my knowledge, I mean you can correct me, the QCT doesn't provide a first principle approach to calculate these functions, but proton distribution functions, but we have these evolution equations which tells us how these will evolve provided we know their existence at some values of q square and x0, okay. So basically these evolution equations determine the PDFs at some value if they're initially known at some other, okay. So the two popular equations which you have heard in last 2 days are the DGLAP equations and the BFK equations. Now the first one only tells about the evolution in terms of q0 square, okay. So if you know the initial PDF at some value of q0 square which is lower than q square, then you can predict the PDF at some other q square, provided you know at some initial virtuality. Now the second one is the BFK equation, which finds the PDF at low x if the value is known at some x which is greater than what you want to find. So now we are interested in low x let's say, functionality of the proton let's say proton structure. So we'll use this, we'll see the validity of this equation for low x. Now what happens, this is the simpler form of this equation. So this is a linear equation, this is the integral kernel, this is the strong interaction coupling constant, and this is the dipole quark anti-quark dipole scattering amplitude. So what you can see from the very let's say very nature of this equation, it is linear, and the solution also tells us that this evolution leads to a power law growth of the Parton distributions. So as you grow very low in x values, you see that the number of partons grows. Okay, so and the growth is like this, it is a power law growth, and where lambda is a positive number. So if this is happening, so what's the issue with that? Suppose we have the number of partons growing as we go more lower in values of x, then what is the issue with that? QCD won't forbid if the densities of parton increases like that. So what's the issue? So what it diverges in what sense?
Power law growth.
So the cross section becomes unphysical, because once you have lot of parton densities, so you'll expect the probability of interaction also increases, right? And probability of interaction will give you this cross section, right? So the cross sections become very large. They go to the unphysical values, but that is not allowed because we have a limit. When remember when we studied quantum mechanics, the calculation of cross section, we talk about the black disk limit and all those things. And similarly in QCD we have that Froza-Martin bound, which tells that the cross section or as a function of center of mass energy that cannot grow faster than, let's say, log square of the center. This is the S or the Mandelstam variable. So, but whatever if you see the solution of this equation, you see that it grows as power law for this square of the center of mass energy. So in that sense, it really violates this evolution equation, really violates both whatever we have studied, the black disk limit as well as the Froza-Martin bound. So what happens, if you see this picture, let this be your proton with lot of, let's say at low x with lot of partons, gluons. So once you go to very low x, so what happens, this gluons splits and that increases their number. But we see if this goes on, that we get unphysical cross sections, okay. So then how to take care of that? So one of the way out is that at very high energies, you can imagine that this growing number, which was scaling like a power law growth, it can be tamed if your gluons recombine again. Okay, so this is the gluon recombination, and it is proportional to the, because you need a pair of gluon for them to recombine to give a gluon. Okay, so in that sense, if you can add this process, so then the equation can become like this. Okay, so then from the from a linear equation, now this is transforming to a non-linear equation, but it is essential to have a physical cross section. Okay, and this equation is known as the BK equation. Okay. So now what is the aftermath, or what is the consequence of this or let's say this modification? So you will see that it really regulates or slows down the small x evolution. So you won't have your gluons propagating or proliferating like anything. And due to this recombination term, the gluon mergers become important. And since it's a quadratic term here, so when the linear term, let's say this term becomes comparable to the quadratic term, we have a saturation scale emerging. So we'll talk about this, what is this? And this depends on x, with this variable where lambda should be a positive thing. Okay. Now what is this scale? Okay, we'll talk about in terms of nucleus. So what we are seeing that this saturation means once you have both splitting at recombination, you will arrive at a momentum scale or QS square scale when these two competing effects become, let's say, compatible and you have a saturated gluon density. Okay. So now this phenomena, what we observed, will also be happening in nucleus because there are also multitudes of protons. So then why nucleus? Why we are going for EA collisions? Okay, so what we saw, this partum saturation is a universal phenomena valid for both protons and nucleus. So why we are picking nucleus for this EA collision? So let's consider a large nucleus. When I say large nucleus, having large A values, and you boost them to very high velocities, let's say ultra relativistic velocities. So again, as they are Lorentz contracted, what will happen for this? So you will have a low X gluons which will be really proliferating in the nucleons inside this nucleus. So once you have very low X gluons, what about their lambda? What about their wavelength? So just apply Heisenberg's principle. If you have very small momentum, the wavelength will be high. So the longitudinal wavelength will be larger. So in that sense, they really, these gluon wave functions, they act like, classical objects. Okay. Now when this is Lorentz contracted, these wavelengths, these gluons, you have a lot of gluons in low X regions, they try to overlap with each other. Okay, and they form a very dense state. Okay, that is which leads to high parton density. So a large occupation number of these color charges, because gluons are colored objects, this leads to a classical gluon field. And this is essentially the CGC picture what Venugopalan and McLaren gave. So they told that this gluon field, what they predicted that this gluon field can be treated classically because they have a larger longitudinal wavelength, and in the sense these gluons, they interact with all the nucleons inside the nucleus because the wavelength is quite large. Now once we have this classical gluon field, this gluon field can be treated as solutions of your Yang-Mills equation. Now if that is done for a single nucleus, you get the distribution. This is an unintegrated distribution of gluons. Okay. So here it is the phi is the distribution function and it is multiplied by kT, which is the transverse momentum, and you plot it as a kT. So this is the theoretical thing which was obtained by solving this Yang-Mills equation for a single nucleus. So what you see here, if you closely observe this graph, what you see that at QS, you have the maximum number of gluons or is the maximum density. Now, if you go to values for KT which is less than QS, you see that the power law increase which was expected now shows a logarithmic behavior, and at very low X, you see that this picture of the gluon distribution more or less saturates. Okay. And the good thing is that this QS is still larger than lambda QCD, so you can use your perturbative calculations to calculate things. Okay. So what we see that here there is an emergence of saturation scale in case of nucleus also, and the majority of gluons in this classical distribution have transverse momentum which is QS, and this distribution, the entire distribution saturates, justifying the name of the saturation scale because we now calculate things in terms of QS square rather than any Q square. Now let's come to, still we are not clear why we are doing this QS. Now these are the gluon transverse momentum, right? Now coming from the gluon fields which are there inside our nucleons at very low X. So at very high energies, these gluon fields, as we had mentioned earlier, they come from all the nucleons inside the nucleus. And once the gluons interact with these partons inside the nucleus, they receive transfer. They can receive transverse kicks from all these partons, and the resultant will be their transverse momentum. But as you know, if you take nucleus, as we have done, as we know from our nuclear physics studies, what is the characteristics of the nuclear density? So if you have a nucleus, what is the characteristics of the nuclear density? It is more or less constant, barring at the edges, at large R, right? So you know the Fermi distribution. So towards the large R, it has a decreasing function. More or less, we treat it as constant, right? Now, if these gluons have to interact with the all of the partons inside this nucleus, then inside the nucleus, it will depend upon how many it interacts with, right? That will determine its transverse momentum. So that will indeed depend upon the radius of the nucleus, right? And how the radius of nucleus is dependent on A? It goes as a to the power 1 by 3. So what we can say that this q square has this dependence. We can easily say that, right? So now if we compare that with the proton, here proton it's 1, correct? Now for a nucleus, this square has dependence on a to the power 1 by 3. So we have an enhancement of saturation effect if we just change from proton to nucleus, right? This enhancement in the nucleus, or this enhancement of the saturation effect in the nucleus compared to proton is called the factor, and it is the reason why we are doing this EA collisions. So what you can see, so that will be clear in the next slide. So let's concentrate on this plot here. So you have logarithmic of 1 by x, and here you have q square. So this is your lambda QCD. Beyond that, you have non-perturbative region or confinement sets in. So we can't do our first principle calculations. Now suppose you have your proton here. So for q square, you can have your DGLAP evolution. And if you want to go to low x, this is the summary of what we have discussed, where the saturation starts setting in as you go more into more low x. So you have this BFKL evolution, and then if it becomes more, then we know how to introduce the nonlinear term so that we have this BK evolution, and then the saturation region sets in, okay? So that's the picture what we have dealt with. And also in nucleus, we are also seeing that the saturation scale is proportional to a to the power 1 by 3. Now, if you remember when we originally started discussing the onset of this dense regime, it was dependent on 1 by x to the power lambda, where lambda was a positive number. So once we go very low in x, your saturation sets in. So that is one dependence. And here what we are seeing that your saturation also increases if you use nucleus instead of your protons. Okay, so we can combine these two dependencies to this one. Okay, so now if you take from Hera and Rick, you also have, so we have seen this lambda is of the order of, let's say, 0.3 to 0.6. So you can combine this QS square dependence as A by x to the power lambda. So it depends upon this A, which is your factor, or if you use a nucleus instead of proton, you get the same saturation effect. But let's say you take a gold nucleus, which is a heavy nucleus. So your Q square, so what is, let's say 197 will be for gold. So 1 by 3 would be how much? More or less it would be like 6. Okay, so you have an enhancement of that factor. Let's say if you write 197 by x to the power lambda, if you take that 1 by 3, so you get the same saturation in case of a heavy ion, which you would have observed in case of protons for, let's say, order of magnitude is 197, so twice for low x, right? So see, going to low x means you have to increase the energy. That is that if you, let's say at collider things, that is quite expensive. So if you want to see the same saturation at available energies, we can use nucleus instead of protons to see it better. Okay. So this is also a simulation here. Here on x-axis you have x, and on y-axis you have q square. Now you can, there's a comparison for proton, calcium, and let's say it's like 40, and gold, which is like 197A. Okay. So you can see that the saturation scale increases as we go to heavy ion compared to your protons. Okay. And here, see, and we also see a dependence on B. B is the impact parameter of the collision. So once you have nucleus, you can have a direct head-on collision. In that case, your impact parameter is 0. Or you can have also a glancing collision where the impact parameter, let's say extreme peripheral collisions where the impact parameter is of the order of, let's say 2R. So in that case also, these are, let's say, theoretical models which gave simulated results for, let's say, for the differences in A value as well as in differences in B. Okay, so when you have head-on or very small values of impact parameter, the saturation scale also increases. So we can probe the same physics, what we are probing in protons, proton or electron-proton collisions, but we are getting the saturation scale. So what you would have got for x values, let's say 2 orders of magnitude less in proton, we are getting the same in A. So this enhancement is the reason why we want to do EA collisions. Okay, so this will be a better way to probe the saturation scale and also to test QCD in nuclear environment. Okay, so far we don't have, because that experiment or the collision has never happened, so which will happen at EIC, but it is also giving us a lot of things to study because all these are model calculations. We don't know how the real data will behave, but definitely it will be interesting to see how all these predictions, theoretical predictions and simulations, how these get compared to the experimental data. Okay. Now let's talk about the nuclear structure function. So we know all about the PDFs that came from, let's say, the proton structure. So now, are the distributions going to be modified if we have a nuclear ambience? Okay, so that is now a bound proton, okay, because inside nucleus the protons or your hadrons are bound. So the PDFs which we are getting for a free proton, will they be similar in a nuclear environment? So the way is to see nuclear structure functions or nuclear PDFs. So we know that the total cross section is related to the structure function. This is what you must have studied. So we have two structure functions, F2 and FL. So F2 is sensitive to your quark distribution function, it's the charge distribution, and FL is sensitive to, this is something which you know. Since saturation is gluon driven, so if you go to very low value of X, so we know that it's gluons who play the major role. So if you do a measurement of FL at very low X, so you know that the FL will have the, let's say, one expects the effect will be probably very high on FL rather than on F2, because here the gluon distribution plays a very important role. Now if that is the case, okay, let's start from the factorization theorem, as you all know, because if there is a hard interaction process where your Q square is much higher than your lambda QCD square, then the factorization theorem tells us that the cross-section of that hard process can be written like this, and they're completely independent of each other. So these are your PDFs which you get. These are non-perturbative, you get it from experimental data, and this is something which you can calculate perturbatively. Okay, so it realizes the convolution of these parts to make the predictions of experimental observables. Now keeping this in mind, so we can define, now this was with hadron and hadron. Now what happens when you include nucleus instead of hadrons. So nucleus is nothing but it's, let's say it's a composite of the protons and neutrons. So for nucleus, you can write Z by A plus N by N, you have these functions, but remember these are the bound PDFs, not the free PDFs, okay? These are the bound PDFs, and we know that the bound PDFs are a bit different. For a proton, it's a bit different from the free. So we have to see that does the nuclear ambience significantly affect the distributions. We don't have measurements, but we can have some low energy measurements of nuclear structure functions. So how do we quantify them? How to quantify the nuclear effects? So the best way is the way we do that, we just can take a ratio, and the difference between a nucleus and proton is that you have a number just for isosymmetry, spin isospin symmetry. You can treat your neutrons similar to that of protons. So your F2A, if you just scale by A, and this is your structure function for a proton, P stands for proton and A for nucleus. Similarly, you can derive two ratios, okay, R2 and RL. This refers to, let's say, this would be mostly quark driven, while this will be mostly gluon driven because of the F2 and FL factors. So since saturation is gluon driven, that was our discussion till now, one expects that the effect of saturation will manifest strongly in, let's say, RL, because it will manifest strongly in FL, and hence we also see that it will be seen in RL, okay. Now these, because these are these can be experimentally measured, so these ratios can be also constructed for quark and gluon nuclear PDFs. So instead of structure functions, you can also replace them by nuclear, by their PDFs, and you can construct ratios like RQ and RG, where G refers to gluon and Q to quarks. And similarly, you expect the effects to be seen, the saturation effects to be seen mostly in RG. So we don't have experimental measurement, but we have theoretical predictions. So, and this prediction is very interesting. So on x-axis you have x, and on y-axis you have the ratio, but with respect to G, because we want to see how, because we know that this will be mostly affected by the saturation phenomena. So on y-axis we have RG. Now it's very interesting because it has a very interesting behavior. So now let's, and you know the x lies between 0 and 1. So if we try to see this entire range, you see that R2 is greater than 1 for x going to 0.8. So here you see this is greater than 1. This is the Fermi motion region because the nucleons inside the nucleus are in constant motion. And then for 0.3 to 0.8, this is the EMC region, okay. This is 0.1, so R2 is less than 1. You can see this region, okay. Now again R2 is less than 1. This is the most interesting region, and let's say one of the substantial evidence of saturation setting in is the shadowing region, okay. R2 is less than 1 for x less than 1, and in between there is an enhancement, it is greater than 1. This is known as the anti-shadowing region. So it will be interesting to do this measurement and compare with the model estimations. So questions which can be addressed with the EIC collisions at this level, whatever we have discussed, is what is the role of strong gluon fields, parton saturation effects, and collective gluon excitations in nuclei? So can we experimentally find evidence of nonlinear QCD dynamics? Because we don't have any experimental results in that, in the high energy scattering of nuclei. We have only scattering of protons, not with nuclei. So we want to see that whether the effects of nonlinear dynamics, which is your BK equation, whether it is still valid for nucleus, and what is the momentum distribution or spatial distribution of C quarks and gluons inside the nuclei, all these TMDs and everything we can do it and find it in nuclei. And are there any strong color fluctuations inside a large nucleus? All those things which we have discussed. So can we have experimental validation using proper observables? So that sets the stage that why nucleus, electron nucleus collisions are interesting. So having said that, let's go to the heavy ion collision regime, where we have this PA collisions. A stands for heavy ions. We have AA collisions, okay? So today I'll talk about the initial conditions, because how you see your ultra-relativistic nucleus is important to predict things with the experimental observables. So initial conditions are very important. So this is a cartoon of relativistic heavy ion collision. So you have two heavy ions accelerated to ultra-relativistic speed, so they are Lorentz contracted. So you see them as flat pancakes. So this initial state, okay, so that's what I'm going to discuss here. So what should one take as initial state, so you can really compare it with the experimental observables. So once they interact, once they collide, they deposit the amount of kinetic energy in the center. So you have a phase of very least understood pre-equilibrium phase, where you have partons originating, then slowly these partons interact to form a nearly equilibrated stage, because that thing is also under a lot of discussion, that whether that stage is thermally equilibrated or it's near equilibrium QGP phase, because it's a stage of let's say quark and gluons, and slowly these quarks and gluons will hadronize to form your hadrons, and after a certain time, when the mean free path becomes larger than the interaction length, they stream out freely and hits the detectors. Okay, so there are different stages in a heavy ion collision, and you have different observables, different probes to or let's say different probe to know about the stages of collision. So, and this happens over a very small interval of time. All these QGP formation and everything happens within 1 Fermi per C. So it's very difficult to probe this scenario, but we have let's say self-generated probes in terms of jets or heavy flavors, which gives us information about the very initial stages of the collision. So we'll come to that later in later talks, but let's talk about initial condition. That means the condition what is here, okay? So the first and one of the very basic approach was given by Glauber, or it's a Glauber optical model. So it's a very simplistic geometrical approach, okay? So the idea is that, so you have two heavy ions, so you have the distribution of nucleons inside those heavy ions. So when they interact, just consider the interactions as geometrical overlap, okay? It's a very simplistic approach. The typical quantum, so once they interact, they'll have scattering amongst the nucleons to, let's say, to give you something which I'll discuss here. So it views the collision of two nuclei in terms of individual interactions of the constituent nucleons. So you have protons, neutrons inside your, let's say, ions. So when they collide, depending upon the impact parameter of the collision, so you will have individual interactions, and that will give you 2-3 things which the model derives. I'll tell you what are those. So at sufficiently high energy, these nucleons will carry sufficient momentum, so that essentially the path is undeflected. So this is again an assumption because they are heavy particles, and the nucleons move independently in the nucleus, and the nuclear size is larger compared to the extent of nuclear-nuclear interaction. So these are the basic assumptions under this geometrical model. So I'll show you a schematic, but before that, since it is very simple, so you have to give certain inputs. So here inputs are also very simple. You have two things. First, you should know how the nucleons are distributed inside the ions. This is something which we know from our nuclear physics, let's say, classes. So this is the typical, like your Wood-Saxon distribution. People try with uniform distribution and other distribution also. So there are options there, but the more realistic one is the Wood-Saxon distribution. So you have to give these parameters just to say how your nucleons are distributed. Because once they overlap, depending upon the impact parameter, this distribution is important. Because that will decide how many participants are there. Okay, because once they overlap, the nucleons have to interact from the target nucleus, they will interact with the projectile nucleus. So when that overlap happens at a certain impact parameter, so this, this distribution is very important. So people sometimes assume uniform distribution, people sometimes assume Wood-Saxon distribution. So you have that freedom to change, but mostly it is the realistic one. So we will stick to this. And then that interaction has to proceed via the cross-section. What is the cross-section of the nucleon-nucleon interaction? So these values also we have to give, and we give realistic values which we have obtained from experiments. So this is because when you collide your nucleus or your nuclei, it has to be at certain center of mass energy. So you have this dependence of nucleon-nucleon cross-section as a function of center of mass energy. So you can fit it nicely and you can obtain the cross-section values at the desired center of mass energy. So once you have these two inputs, you are set to use this simple geometrical model. So this is the projectile, this is the target, this is, let's say, a realistic scenario depending upon the impact parameter, the number of participants and the number of collisions are decided. Okay. So these are the calculations which go into this simplistic model. So you consider your two heavy ions which collide at relativistic speed, and you also decide the impact parameter. Remember, all these things are not measured in experiment. We can't measure what is the impact parameter of the collision, okay? But you'll see the simple model giving beautiful results when we compare it with experimental data, okay? So this is what you do at your theoretical level, and it's easy. One can easily do these calculations. So the probability of the overlap area is given by this. This is the density of the nucleons inside. Let's say if you can treat A as the projectile, then B, or whatever, target and projectile, you can denote whatever you want. So this is the initial density distribution. So then the joint probability per unit area of interaction will depend on the impact parameter. So that will give you the joint probability. These are the individual probabilities when they interact. Is basically the overlap function. So once you integrate over the values of, let's say, the effective area, you can get this TAB, which is also known as the thickness function. And once you know, because once you know the thickness function or the number of nucleons inside the overlap area, just you multiply by the inelastic interactions, because that will tell you the strength of the interaction happening. So the probability of an interaction is given by this. So, and the probability having n interactions, just use a typical binomial thing. You have to assume this binomial distribution, treating them as individual, let's say, independent interactions. So that will give you the probability. So the total probability can be given, just treat the binomial distribution discretely and you can get. So the total interaction cross section is given by this. So just by knowing the NN or the hadron-hadron interaction, you can get the nucleus-nucleus interaction by this simplistic picture. But let's see how true it is to the real scenario. So once you know this interaction, you can find the number of participants. When I say number of participants, it is the number of nucleons which interact in the overlap region. Okay, so your collisions can be this, can be this. So depending upon whether they are peripheral, and when this is head-on, those are known as central. So depending upon the collision, these colored ones are like the ones which participate in your interaction, okay? And once, this is the number of participants, okay? This is a very important quantity which you don't get experimentally. Then once you have nucleons participating, they'll have number of collisions. So this is given by number of collisions, which is also not determined experimentally, and this is the inelastic cross section, okay? So these three quantities can be easily fetched by this simplistic picture. Now let's see how this relates to real experimental scenario, okay? Now this is a simulation, this is the global simulation. So you have the impact parameter distribution. So let's say for a lead-lead or a heavy ion or gold-gold nucleus, mostly the impact parameter lies between 7, the radius is 7 Fermi, so within 14 Fermi you'll have the impact parameter, and that is also seen here. And this is the distribution of, let's say, events in a global simulation. This is not real data, okay? And this is in a heavy ion collision, and this is the n part, number of participants. So once you see once the number of participants are more, the probability, because on y-axis you have this events, so you have more events where the number of participants are less, but when the collision is head-on, you have the probability is less. This is what your model is giving you, okay? Now with this model, and this is the data, this is the actual lead-lead data. So this is the multiplicity distribution. This is something which we can measure. So when I say multiplicity, that is the number of charged particles produced in a collision. Now suppose if you have a central collision where the number of participants are more, so then what will be the multiplicity? It will be highest, right? Because you have the largest number of participation coming from the, let's say, interaction between the participants, right? If it is a peripheral collision where the overlap area is less, what would be the multiplicity? So measuring multiplicity would be an indirect way to estimate the impact parameter, or the number of collisions, or the number of participants, right? So in experiments, we'll measure the amplitude or the multiplicity. It's amplitude because it is showing the detector's amplitude, okay? So if you see, just compare the number of participants, it's nearly 400 for, let's say gold, it's 197, 197, so it's a bit less than that. So if you see the behavior, okay, here also the multiplicity behavior in data is similar, right? Once the number of participants are more, extreme end of the x-axis, you also have the highest number of particles produced. So depending upon the overlap region, you can really, let's say, classify the entire distribution at different percentages of the total cross section, okay? So when I say 0 to 5%, that means it's the 0 to 5% of this histogram starting from the highest value, okay? So this refers to the top central collision, or let's say the head-on collisions. And similarly, the low multiplicities, which is like 50 to 60 or 60 to 80, they refer to the peripheral collisions where your multiplicities are low, or the number of charged particles produced by interactions are low, okay? So what you see, this is the real data, and this red line, okay, this red curve is the expectation from a global fit. So NBD, it's the negative binomial distribution because that tells you the distribution of the multiplicity generated by a single nucleon collision. So what people have observed that in PP collisions, this distribution explains the multiplicity. So when you convolute with the Glauber fit or the Glauber distribution, because n part is something which you get from Glauber models, n collision or the number of collisions, you get it from Glauber model, and when you convolute with the probability distribution function, which is negative binomial distribution in this case, you can explain the experimental data very well. Okay, so one can use that simplistic Glauber picture to really give you the multiplicity distribution in heavy ion collisions. Okay, that is one of the success stories. And here also, just extending that to real data, on x-axis you have n part, Now this N part is obtained from Glauber model because you cannot determine it experimentally. And here there is, so one can ask how it has been plotted with real data. So you have charge particle multiplicity, you do a simple mapping with the Glauber N part, and for a typical charge particle multiplicity, you can have the average number of participants. You do a simple mapping. On y-axis, you have the experimental measurement of dN charged by d eta. As in the talk in today morning, you know what is pseudo rapidity. So it's basically the charge particle multiplicity density is the number of charge particle, and this is eta, so it's the pseudo rapidity density, and you just scale it by n part. So this is the experimental measurement. So the solid points are experimental data, and all these three are different parametrization of this experimental data using Glauber model. So you can see that, I mean, these parametrization works differently in different regions, but more or less they are in good agreement with the measured data. So that is also a good thing to see, that you start with a very simplistic model of heavy ion collision, a geometric model having, let's say, no QCD, nothing, but you are getting a very good, let's say, agreement with real experimental data. So, okay, I can take, let's say, a few minutes more so that I finish the initial condition. This is something which we have already discussed. So, color glass condensate. So, as I explained initially, initial part of my discussion, as you increase the energy, suppose this is your proton, as you increase or accelerate your proton to ultra relativistic energies, you get different snapshots at different values of energy. So high energy means you can probe low x, and you see this is, let's say, gluon, let's say it's totally saturated by gluons. Okay, so this picture, this is the picture of, let's say, nucleus when you move to very high energy. Let's say here it's shown hadron. So even if you go to nuclear level, you will see that this should be the initial stage of collision as per QCD, because at ultra relativistic energies, your protons can look like as gluon dandelions. So your nucleus will be also multitude of these gluon dandelions. So, and this stage, this initial stage, remember in Glauber, we had our typical nuclear components. But now in this color glass condensate stage, we don't have individual nucleons, but glue balls, like gluon dandelions, because at that energy we know that this we can map those fluctuations. We can really take snapshots of hadron as this. Now this is, we had discussed earlier, this is a high density, largely gluonic matter that is associated with the wave function of an ultra relativistic proton or nucleus. Okay, so you can also treat your initial state of the colliding nucleus as, you know, as this color glass condensate. Now, why the name color glass condensate? Colored, you know, they are gluons or colored objects. Okay, glass. What separation of scales?
Large x part and the small x part. For the large x part, they will behave like a static currents, and for the small x partons, they behave like classical fields. So the interaction scales are different, so they behave like glass. And in glassy objects, we know the separations of interaction scales are different.
So in larger time scale, you know, your glass is amorphous. For when the time scales are larger, it behaves as a liquid because the evolution is very slow, right? Otherwise, in some small time scales, we treat glass as a solid thing, right? So in that sense, here also the gluon evolution, once you really go to very low X regime, the gluon evolution times are very large, so you can treat them as glass. And also there are other reasonings where they really compare it with, let's say, I forgot, a spin glass or something like that. So you can easily understand in terms of your, let's say, normal glass, when we treat like with the scale, let's say evolution scale, you can treat this as a glass. Condensate, because it's a saturated state, and we know that the gluon wave functions, they overlap to form a gluon condensate. So normally this state is known as color glass condensate. So you can also treat your, let's say, incoming heavy ions as two color glass condensate plates. Okay, plates because they're Lorentz contracted. So if you do that, okay, yeah, this is. So this is with increasing energy, because with increasing energy you have multitude of gluons here. So the small x parton wave function is dominated by gluons, which populate the transverse area of proton, creating high density of gluons. So that is the state which we have already studied. Now if we treat our heavy ions as incoming two, let's say, color glass condensate. Okay, let's forget about this for now. So this is a picture first given by, let's say, McLaren and Venugopal. So what they suggested, as gluons are added to high energy particle wave function, because we know that at high energies the proton wave function is majorly gluonic. So where do they go? So because the hadron size is limited, it's not that your proton or your nucleus will become big or their size increases. So what they suggested, that once these gluons get added via splitting of the initial gluons, so they'll soon pack the area of the hadron. Okay, so that means either you will soon achieve saturation, but this process can go on forever if you're packing in gluons of smaller and smaller size. So this is just a theoretical idea to say that, to define your saturation scale. Okay, so what it says, that it corresponds to the inverse size scale of smaller gluons which are closely packed. So as you go higher in high energy, what you see that this nucleon is packed with gluons of smaller size. So when we say the onset of dense regime or saturation has happened, it means that, it doesn't mean that the number of gluons have stopped growing, because you see that the cross section has to grow as a logarithmic of square of the center of mass energy. So it only means that gluons of size larger than 1 by q sat have stopped growing. So you can still have small sized gluons. So this is a picture to understand how the gluons are packed inside the hadrons as you go to very high energies, or let's say very low value of x. Now let's see how this initial state compares with the experimental data. Okay, now this is well, let's see what this figure shows you. Concentrate on the left hand side plot. So the x-axis is Pt and y-axis is the number of charged particles. So it essentially shows the transverse momentum spectra of charged particles produced in pp collisions. Okay, so here pp collisions at LHC energies. So this is the acceptance of the detector, and this is measured by CMS experiment, and the results are for two different center of mass energies. This is what the plot shows. Now, and here this is the estimation from, let's say, B stands for impact parameter and CGC is the saturation picture. So it is 7 TeV. So the protons are relativistic here. So they treated protons as, color glass condensate plates, and they did the calculations, and you can see that the distribution of the transverse momentum, which is your transverse momentum spectra. So the estimations from color glass condensate is in well agreement with the measured data. So it's a good way to see how this model agrees with experimental results. Now let's focus on the right hand side of the plot. So on x-axis you have the number of charged particles produced, and on y-axis you have their mean PT. Okay, so, and here it was only for, on the left hand side was for PP, and here it is PP collisions as well as measurements. No, it is also PP. So I think so lead is on next slide. Now this is from a different experiment, Alice experiment, for different values of let's say beam energies, and you see that the mean PT you extract from the transverse momentum distribution only. So here also you see that the estimations of color glass condensates are in good agreement with the measured data. Okay. Yes.
What is the process actually? PP going to what? What are they measuring?
PP going to hadrons.
Hadron.
No, it is not identified particle here. So kaons, pions, protons, whatever.
Inclusive PP
hadrons,
collision.
Yeah.
Okay.
So I could have shown other observables. Since I have not explained the nuclear modification factor of flow, I am not showing them. This is easy to understand because it is transverse momentum distribution or charge particle multiplicity, which we all understand. Okay. So there are also good agreements with different observables, but for these, let's say these two models, I am showing the observables which are easy to understand. Let's say transverse momentum spectra or mean PT of the produced hadrons. But remember, these two are all for PP. Now this is a plot which shows the same, but here now you have lead-lead collisions, P-lead collisions and PP collisions, okay, at different center of mass energies. So you have two CGC plates colliding with each other, or let's say interacting with each other. Then PP already we have seen before, and P-lead is also a type of collision which is done to disentangle the initial and final state effects. So we have three different systems, three different energies, and then you also estimate and you try to see how this mean PT versus the let's say charge particle multiplicities are let's say explained by the CGC model. And we see, let's say green refers to lead-lead collisions. It's a good agreement barring in this region, but more or less it nicely describes the data. It's a very good agreement for P-lead data, and PP already you have seen, but for let's say very high charge multiplicity there is a departure, but we also don't have data. So more or less we also see that this picture of treating your relativistic nucleons or nucleus as color glass condensate plates is also good, and it gives good agreement for different experimental measurements. Okay. So I'll stop here because I'll stop at initial conditions. So the take home message here is we need to unveil the collective behavior of densely packed gluons under conditions where the self interactions dominate. So this is a dense region where this non-linear QCD supersedes conventional linear QCD. So this is all theoretical what we had studied. So we need experiments to see whether these can be validated by data or not. And next thing is the reason why we are using a nucleus. We saw that nucleus is an efficient amplifier because we also see saturation in proton, but we see nucleus amplifies that let's say saturation scale. So nucleus is an efficient amplifier of the universal physics of high gluon densities, allowing us to study the saturation regime in E+A collisions. Okay, so with this I end my first lecture. Tomorrow we'll talk about relativistic hydrodynamics and other observables. Okay, thank you very much. Now it's open to questions.
Actually, I have another question. So you showed that factorized formula for nucleus collision where you introduce the nuclear PDFs.
Yeah.
I am interested to know, has that factorization theorem, is it proven or is it an assumption for nucleus
Still an
collision?
assumption.
It's an assumption?
Yeah.
Okay.
Normally for PP hadronic collisions we use that factorization, but we don't know how those PDFs will behave in
I see.
nuclear reaction.
Thank you. Okay, if not, let us thank Sadhana again and we meet again tomorrow.